आज या व्हिडिओमध्ये today we will see we will first revise what was there in the first chapter and then continue with back of the envelope estimation. In the first chapter, we started from just one single user and then scaled our system to millions of users. At first, our web server and database, all of them were in just one server, and we were routing our requests. There was no load balancer. There we were routing all of our requests to the same server. But then web. We split the web server from the data server and created a separate database. And that was the next step. Later we separated our later we separated our web server web layer from the public internet by using the load balancer, and so the only the load balancer was accessible from the public internet, and uh, and the load balancer had an internal IP address which was used for communicating with our own servers. So the request flow was basically in the beginning. The request flow was the user typed our URL, then got the our server's IP address from DNS service, and then contacted us uh, for the resources. Then we changed the system. For that, we introduced the load balancer. So when the user typed our URL, they received the IP address of the load balancer, not of our servers, but of the load balancer. Next, then we split the database. So when the user's request came for some resource and we needed some data from the database, initially we had it on the same machine, but then we split our database on a separate machine. The database could have been NoSQL or a SQL database. If we wanted very low latency and very high scalability, then we should proceed with having a NoSQL database. Later, we so after splitting the database, we faced some issues. So later, we introduced caching. For the caching, we did caching at two levels. First was at the level of for static content, which was like HTML, CSS, JavaScript. Those things were cached on the CDN, and the database queries, which which were more likely to be used in as per our policy, whether LRU policy or LFA policy, which were more likely to be used in the future, were stored in a cache like Redis. So all the caches give two APIs, cache.get and cache.set. We also have to set eviction policy and expiration time for the cache. Then we proceeded. Now our request flow looks like the user gets our your load balancer's IP address from the DNS contacts for our contacts or load balancer. Then the load balancer would redirect the request for the static resources to the CDN, which would be the closest. Then the user's client will contact to the load balancer, sorry, the CDN, and get the static resources, and then authentication and all other things will be performed by our web layer, which is separated from our data layer in the previous step. Next, we separated our authentication part, like by using a shared storage. So it was a separate storage from our database. Then we implemented multiple data centers. Then we replicated our same setup on multiple data centers like Europe, India, China, USA, Korea, Australia, that way, depending on the number of users we had in each region. And if any of the region goes down, then we will have then the load balancer would redirect the request to one of the other servers. So while separating the database layer, I forgot to mention that we used a master and a slave layer. So there was one master database, and there were multiple slave databases. All the read requests were forwarded to the slave databases, and all the write requests and update requests were forwarded to the uh, were forwarded by the web services to the master database. If the master goes down, one of the slaves will be promoted, or we could have a multi master setup, and for the and so if one of the slave if the last slave goes down, all the requests will be answered by the master. Next, Next, we had some long-running tasks, for which we used a message queue, and the web service will put the task in a message queue, and our workers will continue to work upon them so that we could scale the workers whenever the load increases. And in the last step, we introduced logging, monitoring, and an analytics into our system. Now we will proceed with the back of the envelope estimation. In system design interview, sometimes you are asked to estimate system capacity or performance requirements using a back of the envelope estimation. It are the estimates that you create using a combination of thought experiments and common performance numbers to get a good feel for which designs will meet your requirements. You need to have a good sense of scalability basics to effectively carry out back of the envelope estimation. The following concepts should be well understood: power of two, latency numbers, and availability numbers. Power of 2, we are all familiar with it. To power 10 is 1 kilobyte, to power 20 is mega, to power 30 is giga, kilo, mega, giga, peta, and tera. Sorry, tera and peta. Kilo, mega, giga, tera, and peta. Latency numbers, which every programmer should know. So L1 cache reference on the same core takes zero point 0.5 nanoseconds, so zero point 0.5 into 10 to the power minus 9 seconds. Branch misprediction at the core level will take 5 nanoseconds. L2 cache reference takes 7 nanoseconds. Locking and unlocking a mutex takes 100 nanoseconds, so zero point 0.1 microsecond. Main memory reference also takes 100 nanoseconds. So main memory reference and mutex lock unlock take the similar amount of time. Compressing 1 kilobytes takes 10,000 nanoseconds or 10 microseconds. So this is almost 1000 times slower. Compressing is 1000 times slower than mutex lock, and main memory references. Sending 2000 bytes over 1 gigabyte gigabits per network takes 20 microseconds. So this is 2000 times slower. Reading 1 MB from memory is 250 microseconds, so this is 25 times slower. Round trip within the same data center is 500 microseconds, so 50 times slower. Disk read is 10 milliseconds. So when the even even a network call is faster within the same data center than a disk read on the same computer, 10, which takes 10 milliseconds. So 10 milliseconds are 100th part of a second. Reading 1 MB from the network takes 10 milliseconds. Reading 1 MB from the disk takes 30 milliseconds. And from sending packet on a round trip from California to Netherlands and back to California takes 150 milliseconds, around 1/10 of a second. Memory is fast but the disk is slow. Avoid disk seeks if possible. Simple compression algorithms are fast. Compress data before sending it over the internet if possible. Data centers are usually in different regions. It takes time to send data between them. High availability is the ability of a system to be continuously operational for a desirably long period of time. High availability is measured as a percentage, with 100% means a service that has zero downtime. Most services fall between 99 to 100%. Cloud providers like Amazon set their service level agreement at 99.9% or above. So if it is 99% availability, then we expect 4 days of downtime per year. Now, for one nine, we expect 9 hours. For two nines, we expect 1 hour. For three nines, we expect 6 minutes. And for four nines, we expect half minute. Estimating Twitter queries per second and storage requirements. Queries per second requirements are very frequent to calculate in back of the envelope estimation. We are assuming that there are 300 million monthly active users. 50% of users use Twitter daily. Users post 2 tweets per day on average. 10% of the tweets contain media, and data is stored for 5 years. Queries per second estimate. So daily active users 300 million into 50%. Total users were 300 million. 50% of that would be 150 million. Queries per second. So 150 million users will send 2 tweets per day, and each day has 24 into 3600 seconds. So around 3500 queries will be like sent per second to our Twitter server, and the peak number of queries would be twice of the average queries per second, which would be 7000 queries per second. We will only estimate media storage. So average tweet size, the tweet ID would be of 64 bytes. The text would be of 140 bytes, which is the limit, and the media would be around 1 megabyte. The media storage would take 150 million users into two requests they do into 10% of the tweets which will contain media into 1 megabyte. So around 30 terabytes of this would be required per day. 5 years of media storage. So 30 terabytes into 5 years into 365 days would be 55 petabytes for 5 years. Back of the envelope estimation is all about the process. Solving the problem is more important than obtaining results. Rounding and approximation. It is difficult to perform complicated math operations during the interview, so we should round the numbers to tens. Write down your assumptions. It is a good idea to write your assumptions to be referenced later. So write down your assumptions is the main takeaway here. Label your units. When you write down 5, does it mean 5 KB or 5 MB? So we should. The commonly asked back of the envelope estimations, queries per second, then peak queries per second, which are which will almost all the time take twice of the queries per second. Storage cache, how much storage would be required for memory, how much cache would be required, number of servers we will need. You can practice these calculations when preparing for an interview. Congratulations on getting this far. Now give yourself a pat on the back. Good job. A framework for system design interviews. We have just landed a coveted on-site interview at your dream company. The hiring coordinator sends you a schedule for the day. Scanning the list, you feel pretty good, except one component: system design interviews. It could be as vague as designing a well-known product X. The questions are ambiguous and seem unreasonably broad. Your wariness is understandable. After all, how could anyone design a popular product hour in an hour that has taken hundreds, if not thousands, of engineers to build? The good news is no one expects you to. Google search is deceptively simple. However, the amount of technology that underpins the simplicity is truly astonishing. If no one expects you to design a real world system in an hour, what is the benefit of system design interview? System design interview simulates real life problem solving where two co workers collaborate on an ambiguous problem and come up with a solution that meets their goals. The problem is open ended and there is no perfect answer. The final design is less important as compared to the work you put in the design process. Let us flip the table and consider what goes through the interviewer's head as he walks into the conference room to meet you. The last thing he wants is to give you an inconclusive evaluation because the session has gone poorly and there are not enough signals. What is an interviewer looking for in a system design interview? An effective system design interview gives strong signals about a person's ability to collaborate, to work under pressure, and to resolve ambiguity constructively. The ability to ask good questions is also an essential skill, and many interviewers specifically look for this skill. The good interviewer also looks for red flags. Over engineering is a real disease of many engineers as they delight design purity and ignore trade offs. They often are unaware of the compounding costs of over-engineered systems, and many companies pay a high price for that ignorance. You certainly don't want to demonstrate this tendency in a system design interview. In this chapter, we will go over some useful tips and introduce a simple and effective framework to solve system design interview problems. A four-step process for effective system design interview. Step 1. Understand the problem and establish design scope. Step 2. Propose a high-level design and get a buy-in. Step 3, design a deep dive. And step 4 would be a wrap up of all the decisions you have taken. So, why did the tiger roar? Yes, Jimmy, because he was hungry. Very good, Jimmy. Jimmy has always been so. We should not be like a student, like the student who answers every question asked by the teacher in the classroom. So, in a system design interview, giving out an answer quickly without thinking gives you no bonus points, and answering without a thorough understanding of the requirements is a huge red flag. Answering without a thorough understanding of the requirements is a huge red flag. The interview is not a trivia contest. There is no right answer. So do not jump right into giving solution. This is extremely important. As an engineer, one of the most important skills is to ask the right questions and make the proper assumptions. Ask the right questions and make the proper assumptions. Gather all the information needed to build the system. So don't be afraid to ask questions. When you ask a question, the interviewer either answers your question directly or asks you to make your assumptions. If the latter happens, write down your assumptions on the whiteboard. You might need them later. What kind of questions to ask? Like what specific features are we going to build? How many users does the product have? How fast does the company anticipate to scale up? What are the anticipated scales in 3 months, 6 months, and a year? What is company's technology stack? What existing services you might leverage to simplify the design? If you are asked to design a newsfeed system, you want to ask questions that help you clarify the requirements. The conversation, is this a mobile app or a web app? How, what specific features are we going to build? What are the, yeah, is the newsfeed sorted in reverse chronological order or a particular order? Each post has a different weight. How many friends can a user have? What is the traffic volume? Can feed contain images, videos, or just text? In this was our step one, when in which we understood the problem and established the design scope. For in the step two, we propose a high-level design and get a buy-in. It's a great idea to collaborate with the interviewer during the process. Come up with an initial blueprint for the design. Ask for feedback. Treat your interviewer as a teammate and work together. Draw box diagrams with key components on the whiteboard or paper. This might include clients, APIs, web servers, data stores, caches, CDNs, and message queues. Do back of the envelope calculations to evaluate if your blueprint fits the scale constraints. Think out loud. Communicate with the interviewer if the back of the envelope the estimations is necessary before diving into it. If possible, go through a few concrete use cases. This will help you frame the high level design. It is also likely that the use cases would help you discover edge cases you have not yet considered. Should we include API endpoints and a database schema here? This depends on the problem. For large design problems like design Google Drive, this is a bit of a too low level. For a problem like designing the backend for a multiplayer poker game, this is the fair game. Let us use a design and newsfeed system. At the higher level, the design is divided into two flows. Feed publishing and news feed building. Feed publishing: when a user publishes a post, corresponding data is written into cache, and the post will be populated into friends' news feed. And in case of newsfeed building, the newsfeed is built by aggregating friends' posts in reverse chronological order. So here is the diagram. The client would contact DNS and get the IP address of the load balancer and make a request that, for example, v1 slash me slash feed slash content equals to hello and auth token. On the load balancer would forward the request to the web server. The web server has multiple services like post service, fan out service, and notification service. It will redirect the request. So in post service, we'll put the post in the cache and then put the post into the database. The fan out service would use the newsfeed cache, and the notification service would send the notifications. Design. So we are now going to do a deep dive. At this stage, we have achieved the following objectives. We have agreed on the overall goals and feature scope, sketched out a high level of blueprint for the overall design, obtained feedback from you, the interviewer, on the high level design, had some initial ideas about areas to focus on in deep dive based on her feedback. You shall work with the interviewers to identify and prioritize components in the architecture. It is worth stressing that every interviewer is different. Sometimes the interviewer may give off hints that he likes focusing on high level design. Sometimes, for a senior candidate, the discussion could be on the system performance characteristics, likely focusing on the bottleneck and resource estimation. In most cases, the interviewer may want to dig into the details of some system components. For URL shortener, it is interesting to dive into the hash function design that converts a long URL to a short one. Time management is essential as it is easy to get carried away with minute details that do not demonstrate your abilities. You must be armed with signals to show your interviewer. Try not to get into unnecessary details. Talking about rank algorithm on Facebook feed ranking in detail is not ideal during a system design interview, as this takes much precious time and does not prove your ability to in designing a scalable system. At this point, we have discussed the high-level design for a newsfeed system, and the interviewer is happy with your proposal. Next, we will investigate two of the most important use cases: feed publishing and newsfeed retrieval. So, the web servers would talk with authentication and rate limiting. The then post service, then fan out service. Fan out service would get friends IDs, get friends data, then build a message queue, input, then put the request in the message queue. The fan out workers then we create the news feed in the cache, and then this was for the feed publishing, and then for news feed retrieval. So that was feed creation. Here, no response was sent back to the user, but here we are retrieving the news feed. So the user sends request to the API v1 slash me slash feed. Then the load balancer would give the way forward the request to the news feed service. The news feed service would talk to the cache, get the user cache, get the user's post cache, feed, post DB, user DB, news feed service, and then send back the response. In this final step, the interviewer might ask you a few follow-up questions or give you the freedom to discuss other additional points. The interviewer might want you to identify the system bottlenecks and discuss potential improvements. Never say your design is perfect and nothing can be improved. There is always something to improve upon. This is a great opportunity to show your critical thinking and leave a good final impression. It could be useful to give the interviewer a recap of your design. This this identify system bottlenecks and discuss potential improvement. This is particularly important if you suggested a few solutions. Refreshing your interviewer's memory can be helpful after a long session. Error cases like server failure, network loss are interesting to talk about. Operational issues are worth mentioning. How do you monitor metrics and error logs? How to roll out the system? How to handle the next scale curve is also an interesting topic. Propose other refinements if you had more time. To wrap up, we summarize a list of the do's and don'ts. Always ask for clarification. Do not assume your assumption is correct. Understand the requirements of the problem. There is neither the right answer nor the best answer. A solution designed to solve the problem of a young startup is different from that of an established company with millions of users. Make sure you understand the requirements. Let the interviewer know what you are thinking. Communicate with your interviewer. Suggest multiple approaches if possible. Once you agree with your interviewer on the blueprint, go into the details on each component. Design the most critical components first. Bounce ideas of the interviewer. A good interviewer works with you as a teammate. Don't be unprepared for a typical interview questions. Don't jump into a solution without clarifying the requirements and assumptions. Don't go into too much detail on a single component in the beginning. Give the high level design first and then drill down. If you don't think your interviewer is done once you give the design. You are not done until your interviewer says you are done. Ask for the feedback early and often. Time allocation for each step. For step 1 of understanding the problem and establishing the design scope, take, give 3 to 10 minutes. For step 2, propose a high level design and get a buy in. That would be around 10 to 15 minutes, 10 minutes. And then do a deep dive into the design of some important use cases. That should take around 10 to 25 minutes. And wrap up, refresh the interviewers maybe that should take around 3 to 5 minutes. So at the minimum, your interview should last 10, 20, 26 minutes, and at max, your interview should last 55 minutes. So 26 to 55 minutes minimum. Minimum 25 minutes back of the envelope estimation, and maximum 55 minutes. So this has been a great session in which we understood the steps to be taken during a system design interview. So step 1 should be understand the problem and limit the design scope, and establish the design scope. Step 2 should be propose a high level system design and get a buy-in. The third step would be doing a deep dive into important one or two use cases of the system. And third should be the wrap up. Before this, we had gone into before this we before this we had gone into the steps like before this we had gone into the steps like mm, before this we had gone into the steps like this. We discussed availability numbers. Then we availability numbers. So say what is mentioned in the service level agreement of our service, like how long our service should be online. And then before that we discussed power of two binary numbers, and we discussed common computational times like nanoseconds, milliseconds, accessing the disk, branch misprediction, mm, then which was in milliseconds batch misprediction, then accessing the disk, doing a round trip in the same data center, reading the disk, accessing the main memory, accessing the database. All we discuss accessing the disk, reading a sequential 1 megabyte from the disk. We discussed that, and all of those things. All very interesting. Next, we will look at designing a rate limiter.